You do? No. Oh, no. All right, so we're going to take a look at hydrostatic pressure and force. Okay, so we have that the fluid pressure is equal to the density of a fluid times the depth. So that makes sense, right? So like if, for example, you've got a little scuba diver down here. Good times, scuba diving. Have you guys ever been scuba diving? What? Have you guys ever been scuba diving? Yeah, it's fun, right? Well, if you've been. But anyways, so you've got the scuba diver, and so the deeper the scuba diver goes, the more pressure, right? And it's also dependent on the density of the fluid. So like, for example, if our little scuba diver is, let's say, 10 feet in water, so there's certain pressure on him, right? But if he dunks himself into, let's say, a pool of caramel and he goes down 10 feet, then the pressure will be greater, right? Because it's all sludgy and delicious. Yes. Okay. So anyway, so the fluid pressure is dependent on those two things.
What if he dunks himself in caramel?
In what? Yeah, that's what I said.
Caramel.
Same thing. That's like saying nuclear and nuclear. Same.
Not really.
Or potato. Tomato. Anyways, okay. All right. So, let's label these. So the fluid density is typically, you use rho, but I think your book uses omega. And then the depth, let's call it h. So omega h. Okay. So then, and then the force acting on one side of our scuba diver or whatever is equal to the pressure, which is omega times h, and then times the area. So this right here is the area. Okay, so let's do an example here of what this looks like. Not a scuba diver, because scuba diver is a little bit too irregular. So let's say we've got the water here, and then we've got. Did what? I did not see that movie, but that sounds way too depressing. I do not feel like dying or watching a movie about death. Because it's almost spring break, so we want happy thoughts.
But if we find the antiderivative of death.
I don't even want to go there. Okay, so let's say this, we've got this block here, and let's say that the block is 10 feet tall. The depth of the block is 3, so the top of the block is 3 feet below the water. And then let's say Joe, thank you. Okay, so let's say you want to find, so let's do first, let's say we want to find, let me go over here. Okay, let's say you want to find the force on acting on the top of the block. Okay, so let's say we color this in purple. So we've got this top of the block right there, right? And we're finding the force from the fluid pressure on top of the block. Yes? So how do I do that? Well, all I have to do is use my formula, right? Fluid density times the depth times the area. Okay. So, the force is equal to, now the fluid density depends on the density, right? So it's a constant. So we won't worry about that, So if it's water, oil, caramel, potatoes, whatever, tomatoes, mushed up tomatoes, or also known as, I was going to say salsa, but sure, tomato juice too. I don't know. Anyways, okay, now what about H? What's the depth of the plate? 3. Okay. 3. Actually, let's do, let's put in the units because we haven't put them in yet. So the fluid density, what would be the units of density if we're measuring in feet? Pounds per cubic. Yeah, because it's pounds per cubic feet because it's volume, right? Density. Okay, and then this is going to be times 3. The depth is in feet. And then times the area, right, of this plate, the top of the block, which is what? 4 square feet. Okay, so that's equal to, so notice that I end up with just pounds, right, which is a unit of force. So I know I did most things correctly. And how many? This is equal to simply 12 times omega, pounds. Oh, because it measures 2.
The area of the top of the
Yeah, because it's square, right? Measures 2. 2 feet by 2 feet. So these are feet.
Can we use SI units?
Well, we could, but this particular example is a British system. We're in America, so. But we'll switch it up too. Not to worry. Not a problem. Okay, so now, was that easy or difficult? Almost too easy, right? Because we didn't really do anything. I mean, we just plugged in some numbers into a formula. Did we use any calculus? No, right? And this is a calculus class, so we have to use some calculus. So the second question, you'll see, presents a bit of a challenge because let's say we want to find the force acting on one side of the block. So now we're trying to find the force on one of the sides. Let's say this one. So what do you notice the problem is with simply plugging all the numbers into the formula? There's a problem. What is it? Yeah, the depth is different depending on where the reason why finding the force acting on the top of the plate is so easy is because it's all at the same depth. But the side is at different depths, right? So then it presents a challenge, yes? Okay. So not an insurmountable challenge because we have calculus, so what are we going to do? What's our strategy? Thinking in calculus. We will break it up into pieces and then find the force on one part and then add them up and integrate, right? Yeah, so okay. It's exactly the same as we always do for when our brain is thinking in calculus terms. So let's write that down so that we don't forget what our strategy. Our strategy, well, actually, let me put it over here. Our strategy is 1, find, actually, I don't really like this mustard color. How about blue? Okay, find F sub I, which is the force acting on the ith slice. So you take a slice here. So this is just some random slice that I chose. And we can find the force on that slice. What's the thickness of this slice? What am I going to call that? Delta. Let's call it delta y because we're going to measure vertically, right? So delta y. Okay, so then after I have that, then the force is going to approximately equal to the sum of all of those f sub i's. And then I turn, so the force is going to equal to the infinite sum, right? Which is equal to the integral of stuff. So we're going to turn the infinite sum into an integral and use the fundamental theorem of calculus. Thumbs up for the strategy? Okay. All right, so now we implement the strategy. So first things first, I need to find the force on this particular slice. So to find the force acting on this slice, I need fluid density. Don't worry about it. I need the depth and I need the area. Yes? Okay. Now, before I do that, I need a, because I'm going to do it in terms of y, I need to place an axis somewhere. So you can put the axis wherever you want. Where would you guys like the axis? So you can put the axis either, like for example, on at water level. You can put the axis at the top of the shape, at the top of the block, or you can maybe put it at the bottom or somewhere in the middle, wherever you feel like. What do you think? Bottom. Really?
If we do it in the middle, can we just integrate from the middle to the top and multiply by 2?
No. Well, in this shape, yes, but that's way more complicated because you have to worry about other things. And besides, if the shape is irregular, like they will be eventually, then not a good idea. Well, you want to be flexible. So let's put the axis at. I know I asked you guys, but I guess I didn't really want you guys to answer. Well, I wanted you guys to answer at water level, so then we would be simpatico. But you didn't. So we'll put it there, and then we'll move it at the end when we're done so that you guys can see the difference. Okay? Now, another thing is that if I put it up at the top, I'm going to point the positive y axis downward. Okay? So down, y, positive, y values. Yes? Okay. So this makes the numbers easier to work with. Okay. So if that's y, then what is the, so I need these things, right? So what is the depth, which is the distance from here to here?
3 plus delta y.
Not 3 plus delta y, it would be,
3 plus d.
no. So you're looking at the distance from the water level to the slice, and it's changing, right? It's moving, so it has to be with respect to y. So what would it be? I think somebody said it. Depth is equal to, so remember your axis is right here, right? Here's my axis. What's the y value right there? Or, well, actually right here. 3, right? So what's the y value from there to there? What would you call it? It's not a number, it's... Are you sure? Does that make sense? So this is the x-axis right there, right? So this point would be at, so here's y equals 0, right? This would be not 3 plus y, it would be just y, right? Right? So this is your axis, right? So from here to here, that's just y, right? It has nothing to do with where the block is. All this is just some point, and because I put the axis there, then that's simply the y value, right? Does that make sense? Okay, so that's just y. So the depth, based on where I put the axis, then the depth of the slice is at y, and then what's the area of the slice? What about what? What height?
Are we doing the same?
Yeah. Oh, but the h doesn't mean height. H is depth, remember? So that's what we just found. The depth is just equal to y. Distance from the water level to the slice is just the y value. But then what about, what's the area of the slice? 2 delta y, right? Because this is 2, right? So this is equal to 2, and then the width is delta y. So then, let me see, let's go down here a little bit. So this means that the force acting on this slice right here that I drew is equal to fluid density times the depth, which we said was y, times the area of the slice, which is 2 delta y, right? Okay, so then if I want to write this as a sum, this would be, the force is approximately, ooh, sorry, I forgot my little I there. The sum from 1 to n of all of these forces, right? So that's just the force of all the slices, right? And so that's an approximation. And what do I do to find the exact value of the force? Yep. So we let n go to infinity. Let n go to infinity. Then what happens to delta y? Goes to 0. And so the force is equal to the sum from 1 to infinity of all this stuff, right? 2 omega y sub I delta y. And that is nothing more than the integral of 2 omega y dy. And what about my limits of integration? Yeah, the limits of integration are the y values that I'm calculating the force at, right? So in this case, if I take a look, my axis is up here. Where does the first y value that I calculate the force at? That would be at y equals to 3, right? Which is right here. So right here, that's y equals to 3. And then it goes all the way to the bottom, which is 10 more than that, which is 13. Does that make sense? So this is from 3 to 13. And then this is whatever that is. This is easy, right? You just find the antiderivative and all that stuff. Yeah.
So there is a constant.
Yes, omega is a constant. Depends on the fluid. So yeah, you don't really worry about that. I mean, you plug it in when you know it, but this is just in general. Does that make sense, the idea? Okay, so let's say we want to move the axis. So this is completely correct. So we find whatever that is. Use fundamental theorem of calculus and all that kind of good stuff. But now let's say I want to move the axis. So let's say I go, okay, I want the axis to be at the top of the block. So right here. So I'm going to get rid of this axis. And now my axis is right here, and then y is pointing still downward. It's still positive, but the water level is still up here, right? So this is the water level, and it's still the same depth and everything. So what changes? Yes, but what else changes before I get to that part? The depth now changes, right? Because the depth, if this is your y-axis is, your x-axis is at the top of the block. Yes? So the depth of this slice, if the distance from here to here that's y, right? Does that make sense? What's the depth? Y plus whatever y is, but then you have to add 3, right? Because you have to add that amount that the block is submerged. Does that make sense? Why? So when I move the axis down there, now in this case the depth would be whatever y is, which is this little distance right here, but then plus the distance from the top the distance from the top to the top of the water to the block, right? Okay, now, but this also means that the limits of integration are going to change, right? Because now, what are my y values going to go from and to? If I look at that picture, this time it goes from 0 to 10, right? So if I were to write this, so this is going to be, if I just kind of skip through all the other stuff, this is going to be the same. And then this y, remember, was the depth. So this is going to be y plus 3. But then it's going to go from 0 to 10. And if you look at those two, if you compare them, they're basically exactly the same, right? Because if you look at the, take a look at the depth, the y, it's saying this, the top one says it goes from 3 to 13, right? And the 2 omega is the same. But if you look at the bottom one, when y is equal to 0, what is inside of the parentheses? 3. And then when you go up to 10, the inside of the parentheses is 13. So it's actually the same exact thing, right? Does that make sense? So that's why it doesn't matter where you put your axis as long as everything matches up. So based on where you put your axis, your depth is going to be a certain expression, and then your limits of integration are going to be a certain expression. So those will change, but as long as everything matches up, then you're good to go. Yes? Okay. Now, so that's nice, but yeah. So it's important to be flexible with the axis, because sometimes you don't get to pick where your axis is. So let's say, for example, you have a plate in the shape of the area. Do you guys want to pick a function? Between, really? That's what my other class said. Oh, x squared. Boring. But okay. All right. Between y equals x squared and let's say y equals to 4. So a plate in the shape of the area between those two is submerged in liquid, whatever, such that the top of the plate is, let's say, 2 feet below water level. Okay. All right, so let's draw a picture. So we have y equals to x squared, so it looks like this, right? And then y equals to 4, so this is what my plate looks like. This mustard-colored plate. And it says that the water level is 2 feet above the top of the plate. So here my water level would be, so what's this value again? Right here? That's 4. So 2 more than that, so that would be at 6, right? Looks like that. So this is in some kind of liquid. Okay. So what's my plan? Force on a slice, right? So you grab a slice. Now our slices, we're going to do, we're going to make the slices always, no matter what your shape is, you make your slices in shape of rectangles. Why do you guys think this is? Okay, the force acting on this slice. Okay, so what do we need? We need the depth. Now, can I put the axis wherever I want?
Yes.
No, I can't, because this function is defined by the x-axis being here, the y-axis being here, and pointed up. So the parabola is formed by the way the regular Cartesian plane is. So you can't move it around. You have to leave it there. So I have to leave it there. So that means that I have to write down the depth based on where the axis is right now. So what would it be? What is it? 4? No, not 4. Nope, it's not y. Because y is
6.
the distance from here to here, right? So that's y. That's the y value of the where my slice is located. So then the depth is exactly 6 minus y. Right? Because so the distance from here to here is 6. The depth is from the water to the point, right? So I have 6, which is the total, and I take away the distance from the x-axis. Yes?
Why is y from to the top of the slice?
Oh, that's where I decided to slice it. Because remember what's going to happen, so the thickness of the slice is delta y, right? And what's going to happen to the thickness of the slice? It's going to go to 0, right? So it's going to be infinitely thin. So that's the point that I decided. Yeah?
Why isn't the depth just 6? Because you have the bottom of the plane at the bottom of the function.
Right, but 6 is the depth only of the bottom of the plate. But you want the depth at any slice, right? So this is just a random slice that I chose. Okay, so the force is equal to density, right? Times the depth, 6 minus y, times the area, which is let's see here. What's the area?
Y equals 4 minus whatever squared.
So it's the length, right, of the rectangle times the width, which is, so the width is delta y, there's no doubt there. But what's the length? 2x. Now I've got a bit of a problem, right? Because I don't want the, you ended class early. That's like cheating. That's like bribing. Anyways, that's my office neighbor. Anyways, you guys don't want to know. All right. Don't worry, we'll have class early too. Okay, so this is a problem, right? Because it's not, I don't want it in terms of x, I want it in terms of y. Okay, so what do?
Oh, y equals x squared.
Y equals to x squared. So x equals to square root of y, exactly. So the area is then equal to 2 square root of y delta y, right? So 2 square root of y, whoops, square root of y delta y. Yes?
What if in this example the plate is between two functions? So how do you decide what y?
Well, the idea is the same, but
How would you change it from x to y then?
well, you would have to do something different. Yeah, I mean this example, this picture that I have up is not sufficient to answer that particular question. We would have to introduce a completely different example. But the idea is the same. Sorry. Not a good answer. But, yeah, this isn't a good time to answer that question. Okay, moving on then. All right, so the force is approximately equal to the sum from 1 to n of all of this stuff, right? Let's put the 2 out in front. Square root of y delta y, right? So then the force is equal to the sum from 1.
Working on sum, do you want us to do like each step?
Absolutely. Very important. Otherwise, it's like when I had you guys do it for the volumes. If I didn't have you do it, then you guys would have no idea how to approach the problem. That's the only reason why we know that we need to cut it up into slices. Okay. So what is it? Sum of 2 omega 6 minus y sub I. We forgot our little sub i's there. Square root of y sub I delta y, and that is nothing more than the a Riemann sum, right? 3-month sum, which is equal to the integral of 2 omega 6 minus y square root of y dy. And then this time from where to where does my
0 to 4.
0, yeah, this time from 0 to 4, right? Because my y values go from 0 to 4, right? Does that make sense? 0 to 4. And that's it. Thumbs up.
Thumbs all the
Okay. Happy spring break. Have a good day.